So applying calculus ideas to the physical world. Okay, so what are we concerned with? We're concerned with displacement, with very often we use the pronumeral x. So distance from a point, but now we have direction, so that's what the plus and the minus represents. Velocity is the rate of change, so v is a logical one to use. Dx to t, the rate of change of x with respect to time. Then there's the dot notation. So this is Newton's notation, and we tend to use the dot notation when we're talking about motion problems, so the mechanics problem. So x with one dot is the first derivative there. And that's the rate of change of displacement with respect to time. So in other words, speed, but now we're saying which direction we're going in, positive or negative. And then acceleration, the next level, so the second derivative if you like. So yes, we could write it as d2x to t2. Also the first derivative of velocity, so it could be dv to t. A simply for acceleration, using Newton's notations, x with two dots, so x double dot, or v with one dot, first derivative of velocity. It's the rate of change of velocity with respect to time, and it's really unfortunate. See, like, we have these words, distance and displacement, so we distinguish which one we're talking about is just the magnitude, which one has direction. And we have velocity and speed. Again, we're talking about just the magnitude, one has direction, but with acceleration we don't. We have acceleration and acceleration, and we use the same word for both. Just a word on deceleration. There is no such thing as deceleration, okay? It's what we think of as slowing down. As far as we're concerned, it simply is when your acceleration is in the opposite direction to your velocity. So it's like this force is pulling you back, so you slow down. You always have acceleration, just which direction it's going in. So here is a displacement time graph. But now, because we're talking about displacement, not distance, we could have negative numbers in the vertical axis as well. We know the slope at any point will give us that instantaneous velocity. So if I want to draw a velocity time graph, it's much like really just drawing a derivative graph. And what do we know about derivative graphs? Well, we know stationary points, so at those two the peak and the trough there, we know that it would be 0 on the velocity graph. When it's increasing, we know it's going to be positive, and so on and so on, and we could come up with a graph like that. And now the slope would give us the rate of change of velocity, so it's the instantaneous acceleration at that point. And then we could then draw an acceleration time graph, which again is just the first derivative of velocity or the second derivative of displacement, and in this case we'd end up with this straight line. And if you look at the actual curves themselves, that kind of makes sense. The first graph looks like what a cubic would look like. And you differentiate a cubic, you get a quadratic. Oh, there's a parabola. Differentiate a parabola, you get a linear function. So it sort of all ties in nicely. So distance travelled then. Well, I can look at my displacement time graph, but it's the distance I've travelled. So all up, I've gone 2 up, then another 4 down, then 1 up, giving me a total of 7 metres I've travelled. Whereas the displacement, how far away from the starting point am I? I'm only 1 unit away, but in the negative direction. So we get -1. Average speed, well, speed is distance over time, so 7/4. Whereas average velocity is displacement over time, so -1/4. But hey, we don't need the graph necessarily. If I've got the formula, I can now work everything out. It's now asking me, well, what would be the formula for acceleration then? Differentiate it once, I'll get a formula for velocity. Differentiate a second time, I'll get a formula for acceleration. So when is it stationary? Explain your solutions. Don't just go, oh, well, 3t squared minus 4t equals 0. Explain why you're doing that. So maybe you make it. Similar to when we're doing curve sketching, we would have said the curve is stationary. Well, now we're saying the particle is stationary, but it's exactly the same. Yes, I could say when the first derivative is equal to 0, like we did in curve sketching, but now I could say, well, but it's when the velocity is equal to 0. That's why I'm solving this equation. And I come up with 2 possibilities, 0 or 14. And I'll answer it in words to actually explain the problem. Yeah, well, okay, it's stationary initially and then again after 14 seconds. This one here, I'm starting from rest and I'm starting at x equals 7. This time they've given me the acceleration equation, 2 plus 6t. We have to find the position. I know the acceleration. I'll go back, I'll integrate to find velocity. Don't forget the constant. I mean, that's going to be real important. Of course, for this one, when t equals 0, v equals 0. Substituting, in this case, the constant does turn out to be 0. I could have got away with forgetting the constant here and it would have been okay. There's v equals 2t plus 3t squared. Now I want to find displacement, but in this case, I'm going to have a problem if I forget my constant, because when t equals 0, x was equal to 7. Substitute in, the constant turns out to be 7. There's my displacement equation. So when t equals 3, I now go and substitute into my displacement equation, and we come up with 43. So there we are, 43. I could say at x equals 43, I could say 43 in the positive direction, 43 to the right. There are all different ways you could say it, but basically you're telling it where the position is. Okay, how do I solve this problem of not worrying about the constant? Well, I do things as definite integrals rather than indefinite integrals. So dv to t, so I'm actually writing acceleration as dv to t, so I can set up an integral, and I'm going to use this idea of what we call separating the variables, which we'll see in more detail later when we look at differential equation. But basically I end up with something like this. It's no different to solving an equation. I'm saying, hey, I want everything with t on one side of the equation and everything with v on the other side of the equation. So I end up with dv equals 2 plus 6t to t, but it's the integral of that. And then I make it definite by just matching up the limits that they're giving me. When time was equal to 0, velocity was equal to 0. So you'll notice on the bottom, I've got 0 matching 0. I want to find an equation that links v and t. So they're my limits on the top. And I'll just integrate. So v, when I see an integral of something like dv going from 0 to v, it's okay to just write v down. If it are the numbers, okay, I might have to integrate, get the value, substitute in. But when we're going from 0 to v, it's fine to just go v. Right hand side, I'm going to do a bit of work though, because I've got to actually integrate these things. 2 will go to 2t, 3t squared, substitute in t, substitute in 0, and we get the equation in a lot less steps. But now here's the beauty of solving the next question, because I want to find the displacement, of course, dx to t equals. If I separate it out, but you'll notice what I've done on the top limit. I've substituted t equals 3 in, because really for this question, I'm not interested in the formula, I want the answer. I can do it all in one go. I just substitute in on the left hand side, and you'll notice now, because I'm not going from 0 to x, I have written it as x, and I'm going from x to 7. Substitute in, but now move the 7 over, I've got the answer in a lot less steps by doing it as a definite integral. So get in the habit of solving these sort of things as definite integrals, and you're probably going to save yourself time. Let's look at some HSC ones. 2001 HSC, there's the formula they gave us, an interesting one. T minus 2 and t plus 2. Starts off with a nice question. What's the displacement when t equals 0? Oh, okay, well, we just substitute in t equals 0. I get negative 1. How I want to answer, I could say x equals negative 1. I've said 1 to the left. Could have said 1 in the negative direction. Show that. All right, well, it's just an algebraic fraction. So I want 1 minus 4 on 2t. If I pull that all together into one thing, oh yeah, look, I do get t minus 2 on t plus 2. I've shown that. Now we want to differentiate this to get velocity and acceleration. So differentiate first to get velocity, tidy that one up. Differentiate again to get acceleration, tidy that one up. Okay, is the particle ever at rest? And give reasons. Well, there's the formula for velocity. I know that that fraction can never equal 0. Constant on the top of the fraction. So no, it's never at rest. Is that sufficient reasoning or not? Debatable. But at least I've explained why I've said no. Look, that can't equal 0. What's the limiting velocity as t increases? Limiting velocity. So well, if it went on forever, t went to infinity, what would this particle approach? In this case it's velocity. So that's what this is asking. What's the limit as t approaches infinity of this expression? And that again will equal 0, because we know that when we substitute in infinity, if you like, not that you can actually substitute in infinity, but when it's on the bottom of the fraction, that's going to end up with 0. Another way I could do it is I could think of the graph itself. If I was to draw the velocity graph, but just for positive t, it would look something like that, because it's hyperbolic going down there, and I can see from my graph that that's approaching 0. So again, I get the same answer. 0 metres per second. 2002, again we're moving in a straight line. Oh, this time it's a trig function. Sketch the graph. I just think this was just a nice way they decided, oh, we're going to make them draw a trig graph. They're sort of forcing you to draw a trig graph. But okay, this is the one we have to draw. X equals sine 2t. Let's find the important things. Amplitude is 1. We've shifted it up 3. The period is pi. I'll mark off my divisions every pi on 4. So draw it all up. And it's a sine graph, but we're winding around 3 instead of the t-axis in this case. And we start at the origin, go up and down, up and down. We've drawn ourselves our sine curve. Using the graph or otherwise, here's the when you have got a graph, if you have got a graph, certainly trig graphs, you don't have to waste time using calculus. You can use your knowledge of the graph. When is the particle at rest? I can look at the graph. I know it's at rest when the velocity is equal to 0. In other words, where are all the stationary points? Well, looking at them, there was one at pi on 4, there was one at 3 pi on 4, 5 pi, and so on. Not a lot of work to do, I just read off the graph. Describe the motions to come up with something creative here. What's it doing? So what did I say? Oh, I used a big word, oscillate. The particle oscillates between 2 and 4, and it's got a period of pi seconds. That pretty much describes what. So applying calculus ideas to the physical world.